Hi, good evening, everybody. Am I audible? Can somebody confirm, please? Okay, okay. Thank you so much. Okay, so welcome everybody to the first DA session that I'm going to be taking. So, this is a 12-week course as we know it. And so, for the next 12 weeks, three of our team members will be joining live for you to interact with. So, yeah, so we'll begin by looking at some important portions of image processing, and then since the course is on computer vision, and slowly we'll transcend into the main agenda of this course, which is deep learning for computer vision. So cool. Then let us start. And yeah, so if anybody has any question in between, please feel free to message on chat, or you can also maybe raise your hand and just ask the question. So okay, let me share my screen then. Yeah, is it visible for everybody, or is it a bit smaller than what you would like? Okay. Yeah. I'll just do that. Yeah. Sure, I'll do that. Okay. Yeah. Cool then. Yeah. Cool. So I request everybody to mute for now. And if you have any questions, just unmute yourself and you can ask. So, yeah, let's begin this session. So the course is called Deep Learning for Computer Vision, but like I said, for week one, we'll start with something a little bit basic, a little bit on image processing. So let's look at some of the topics that Sir has already gone through for this week. So first of all, we'll visit this notion or this concept of histogram equalization. But before going into that, can anybody unmute and tell me what a histogram is? So what does this particular plot mean to you? Does anybody understand this? Hmm. Correct. Right. So in the image context, what do you think it's going to be? Hmm. Good. So, yeah, like our friend pointed out, so histogram for an image is basically nothing but collection of these bars for every pixel intensity starting from 0 to 255. So this particular this particular plot means what? That the zeroth. Okay, I'm going to be yeah. Oops. Yeah. Yeah. So this means what? That you have all these values 0 to 255. Suppose this particular bar means that 0 has this many count, 1 has this a little bit higher, 2 has a little bit higher, and so on. And similarly, if you take this to be the last one, 255, then these are all the individual counts of the individual pixels. So that is what we mean as a histogram of an image. Right. Now you can see one thing that yeah. So now you can see in this particular graph one thing that um, so so if this intensity scale is divided from 0 to 255, you can see that for some of the values which are near 0, they have some non-zero values. Some of them which are near 1, they have some non-zero values. In between here or here, all of these are zero values. So that means what? That in whatever given an image, given a certain image, my the count of each individual pixel varies across the entire range of 0 to 255. Okay, so it's something that looks like this, but if you go by the name histogram equalization, what do we want? We want all the pixels to be equally present, and we'll see that if we are able to do that, then our image becomes so much more sharper and clearer. So again, histogram equalization means what? So we have unequal distribution, some other distribution of pixels in the histogram, and all we want is for to make this particular histogram uniform like this. So coming to the Y, yeah, sorry about this. So coming to the why this is required. So you can see that this is some image that we collected. So this is the original image. And you can see that it's very, it's not very clear in nature. So it's on the brighter side. Most of the pixels are close to the value of 255. So not many. So what has happened is this particular branch, this is a looks like a flower. So this can't be distinguished that much from the background. So now, if you do this histogram equalization, so basically for this, what will happen if you compute the histogram for this particular image, all your so in this particular plot, the most weights, the most mass will be somewhere here towards the brighter pixels. So now histogram equalization will ensure what? That I give so all my pixels from 0 to 255 will have some mass, and we'll try to make them as equal and as equal as possible. So if you have done something like this, then your his equalized image looks so much better. So now you can distinctly see this branch and the flower, and the you can separate it from the background very easily. So right. So this is again what I've been trying to say for the past 2 minutes. That so this was your original images histogram. Suppose this was the histogram of this image, and so you can see that in 0 to 50 there is hardly any population. Then 50 to 100 it's less, and some peak is there around 120 to maybe 200. So these are the most commonly present pixels in the image. And now what you want is for the histogram equalized image, you want that first of all, they should span the scale from 0 to 255 fully. That is the first requirement. And second is they should be much more uniform. And instead of this peaky sort of thing where some have zero values and some have non-zero values. So histogram equalization, so theoretically, if we go for the for a continuous distribution, which I'll show in a bit, we can achieve fully uniform distribution. But for the discrete case, we cannot achieve full uniform. So all the pixels won't have same weightage in the histogram, but you'll get something which is approximate and which looks like this. Let me admit, yeah. Cool. So now, so who can unmute and tell me, like, suppose you want so what do you want? You want a uniform distribution, right? So does anyone remember rather from their probability class, what is the CDF of a uniform distribution? So can anyone unmute and tell me? So remember, uniform distribution has that constant probability for across all the points where it's defined. So what is going to be the CDF of that? Okay, so its CDF is yeah, it can be approximated by something to this effect. So this linear line. So this is what we want to achieve. So we show some proof of what the histogram. So once we equalize the histograms, what the CDF is going to look like, we'll show that in the next slide. So here is some derivation actually that we have put up, which actually shows that what you can do to make a normal image, to make the histogram of a normal image equalized, right? So consider this. Let I be an image with some pixels. Okay, so I is a m cross n matrix. So now for now we'll assume that an image is nothing but a matrix where the dimension of the matrix is m cross n. Okay, so each of these dimensions will contain some pixel intensity, right? So now let's define something. One is what Imax. Imax is nothing but the maximum intensity value, which we are taking to be 255 here, which is the globally accepted constant. And let h of I be the image histogram that we originally have, right? So okay, so now what we want is we want a histogram equalized image, and to do that, what we'll do is we'll simply take this I hat ij is basically your converted image. So what should you do to a given image so that its histogram is equalized? So you take the Imax of the original image, which is the maximum intensity value that we take for the image, which is basically 255 in general, and you multiply it with Cp of ij. So this is P of ij. Now what is C? C is nothing but your CDF for the histogram that you have. So let's go through this formula once again. So what is Ck? Ck is basically 1 by m cross n into summation L equal to 1 to k, L equal to 1 to k, h of L. So h of L we call, so 1 by m of n. Why are we doing that? Because CDF is it ranges from 0 to 1. So we need to normalize. So that is why this 1 by m cross n. And this summation is what? This is nothing but you start from the pixel value maybe 1, and you have a certain pixel value k. So you'll keep on adding all the histogram counts that you have from 1 to k. And that summation you are normalizing with m cross n, and that is giving you the Ck for the pixel intensity k. Suppose k equal to something like 200 here. So now what you will do is at the original, so you take the image that you want to convert, and this output one I hat I comma j. So what you do, you take this Imax, multiply it with C of this. This is the original intensity at position I comma j, right? So you go to this table that you computed for each pixel intensity, and you pick out the value, the corresponding intensity value present at the ij of the original image, and you simply multiply these two, and what you get is the histogram equalized image. So this is how we do it. So simply put, what we do is we multiply 255 with the CDF of the original image. That's all that is required to get the histogram equalized image. And right. So now let's see a simple proof of why this is working. So till now what I have said is something like, suddenly I've given you a cumulative CDF, and I'm saying that you just get the CDF at the correct pixel intensity and you are getting a histogram equalized image. So let's look at the why part, why this is happening. So so to do that, we'll refer a little bit to probability theory. So let's see why this formula works. So suppose your C, which is your this function. So this is some sort of transformation on the original histogram H, right? And say PC is the PDF of C, PH is the PDF of H, right? Now I'll not go into this, but this comes from the probability theory that if you have two random variables such that one is the transformation of another, then this formula holds. So you can find the PDF of C from PDF of H, and by multiplying it with this quantity. So I'll request everybody to go back to probability theory and just look it up. So this formula is very valid. So now so C, we already know the value, right? We saw here already. So remember one thing. So since we have PDF here, so we are considering the continuous distribution at this point in this particular slide. So to prove theoretically that our formula works. However, in the image space, things will become discrete. That's why these integrations will be replaced by summation, right? So if we look at the integration space, that is a continuous space, what do? we so this is the formula for yeah, so this is the formula for C, right? So this is the cumulative distribution function, and this is the hx. So hx is your nothing but your histogram of the original image, and you are integrating it from 0 to k and dividing by m cross n to normalize the entire thing. So now so if you want to do this delta C by delta H, what you do? So basically what? So this one by m cross n comes out, and this thing once you if since this is the CDF, if you find the derivative of it, this becomes nothing but the PDF, right? PDF of sorry, derivative of CDF is always the PDF. So if you find this derivative, this is what you get, right? So now if you put the correct things here in this formula, you'll see that PC is equal to 1 by m cross n. So this is a constant. So that means what? The PDF of this C is a constant, which is a uniform distribution, right? So this is how we show that if we set the output image to be of this formula, Imax cross this thing. So Imax is basically nothing but a scaling factor. So you are ensuring that your image still lies between 0 to 255. Otherwise, if you ignore this, so if you set your image to be the cumulative distribution function of your of the original image at the position, I mean the pixel intensity at position I comma j, you get a histogram equalized image. Okay. Yes. Correct. So now let us look at some examples. So you can see this image, which is of my institute ISC. So it's a pretty dull image of the main building that we have. So the background and the foreground are almost very similar, and both are very dark in nature. And if you find this is easy to understand, this histogram. So because this image is so dull, so dark, that's why all the pixels are mostly concentrated on this part. So from around, say, suppose 30 to 100, something like that. So all the pixel intensities are somewhere concentrated in this area, right? So right. So now what you do is you take this mass that is there and you spread it across all the entire range from 0 to 255. So your once you do this histogram equalization, it becomes something like this. Again, so theoretically for continuous cases, we are able to achieve a complete uniform distribution. But when you approximate it for for the discrete case, you do not get an entirely uniform distribution, but you can see that they are pretty close to each other. So now the image that you get as a result is something like this, where the contrast is so much better and it looks so much better than this particular image. However, there is one example where so let's see what happens here. So can anybody tell me like whether histogram equalization will work here for this particular image or not? Okay, Anirudh, can you tell me why this will work? Can you unmute yourself maybe? Okay, I'm not sure, but what probably false looks means, but it's okay. So, so see, if you do a histogram equalization here, what has happened in this particular image is that you only have a very tiny portion of the image where the lion is a little bit visible. Otherwise, all the pixels here are black. So what has happened is you have so many pixels in this image. So this is like 500 cross 700. So 35, so 3.5 lakhs or 35,000, something like that. Number of pixels are there. So yeah, so there are so many pixels in this image, and you can see that a majority of those pixels are assigned to the pixel 0, right? Sorry. The majority of those intensities are basically here. So most of them are 0. So in that case, if there is a peak like this, which is pointing towards something very constant, this is what we see when we apply this algorithm. right? So all it does is it moves this one from here to here, and your image, instead of becoming the clearer ones that we saw here from here to here, it becomes something like very bright, because you can see that the intensity has peaked here, so somewhere around 200, and it has become a brighter version of your original image. So this is a plain simple scenario where histogram equalization fails because it doesn't work well with cases where you have peaks, which are, I mean peaks on single intensity sort of. So yeah, that's no problem, Anirudh. So is anywhere? Okay, let's admit all. Cool. So okay, so now we have gone through histogram equalization. So let me ask if any question is there from anybody. So please let me know. Okay, if not, then we'll move to the next topic. So, yes, so now that you are going to study deep learning, you'll know that the central idea of deep learning is something called a convolution neural network. And for going into that, we must understand what linear filters are. Linear filters are key to convolution neural networks. So these are nothing but this grid of numbers, right? And they are not random. They are there for some functionality. So what they do is they operate on the image in a certain way. So what you do is you place this particular matrix, 3 cross 3 matrix, on the first 3 cross 3 window here, right? The first 3 cross 3 patch that you see here, and you multiply the individual values here and sum it up, and that becomes the final value for this particular window. Okay, and similarly, then you move your window here to the second 3 cross 3 that you see, third 3 cross 3, and so on. So you repeat it. Once you are complete with the first row, you move on to the second row and take the corresponding 3 cross 3 patches. Take this, multiply the individual elements with this particular filter, and then sum it up, and that becomes your final value. So like I said, linear filters are something that are not random in nature. Oops, yeah. Yeah, linear filters are something that are not random. These are not random numbers. Each of these numbers have some meaning. So you are trying to manipulate your image in some sense using such a filter. Okay, so example, okay, so now let's, like I said, these are not random numbers, right? So we look at some examples maybe. So let's look at the particular filter we took. So why this is important, we have to understand. So this is the filter, and now we can uh, convert it into this plus this, right? So like, can anybody tell me what this filter is doing? If you superimpose this particular filter on something on the image here, say suppose take the first grid, what value we are getting and what it means. Right. So like Anirudh says, it's going to be 4. Why? Because yeah, it's obvious, because you have all zeros. Yeah, yeah, because you have all zeros and a central one. So what that means is that, so generally when you deal with filters, so one thing that you have to remember is that you, like I said, you do find the product, you multiply, and you get the value, and you get the sum basically, and that is put. So now what happens to the output, right? So this value, whatever you get, where do you put the output? So where do you put the value? So that value corresponds to this central pixel, right? So wherever you place this filter, since this is symmetric in structure, it's 3 cross 3. So wherever you put it, the value that you get after doing this dot product, doing this multiplication and summation, that is basically the value corresponding to the central pixel location of this 3 cross 3 patch that you took. So I assume everybody is aware of that. So that's why this means what? That this filter is doing what? It's simply taking your the central pixel that is there in this particular window and giving it back, because it's multiplying that by 1 and all the rest are multiplied by 0. So, and now, okay, there's a question I can see. So, yes, Sandeep, this the recording of the session will be shared with you. Yeah. Okay. So now this particular, the name is already written here. So this particular filter again is a very special one. Okay. So it has already been yeah. Anybody? Okay, yeah. So this particular filter is a very special one. So what is being done here is that if you again, so I'm trying to show you like what will happen if you multiply this filter with this particular matrix. So what it does is it basically multiplies the central pixel with 4, and all the pixels in the neighborhood are multiplied with minus 1, minus 1, minus 1, minus 1. So if you see intuitively, what it's trying to do is, if the central pixel, um, can everybody unmute please? I'll do it. I'm sorry, mute I meant. Yeah. Okay. So yeah, so what I meant here is that your central pixel has a weight 4 and all the neighboring pixels around have a weight minus 1. So what we are achieving by this is that if your central pixel is very different from the pixels around this, it's from the pixels in its surrounding. It basically makes sure that the difference that was there previously, that increases further, right? So that means what? That something that was already different, some pixel that was already different than the neighboring pixels, they are, I mean, they were already different, you are making them even more different. So what that leads to is more sharpness in the image. Okay. So this particular filter is called a Laplacian. So you can again go back to the course notes to understand the nitty-gritties of it. So basically, this is obtained by doing a second derivative on the second derivative. So second derivative of the image. So wonderfully, you are trying to do a second derivative of the image to detect the edges, and quite wonderfully, this particular neat filter turns up. So this is called a Laplacian filter, and you use this to make. Uh, does the matrix represent intensity of the pixel? No, no, no. So this is not a intensity sort of. These are all numbers which are very very typical, and they are basically they'll help you. Okay, where do I find this? Okay, it's not coming. Oh, here. Okay. Yeah. So these are all typical numbers which basically play on top of your pixel intensities, and then they try to change it a little bit. Okay, so that your image changes to some extent. So here you can see that this was the original image. Now, if you place the Laplacian, so these are all typical Laplacian masks. Okay, so central pixel you can see is very something very positive, and the ones around are pretty negative. So here also this is another Laplacian mask. So now, yeah, so this is a typical, this is suppose some image, right? And this one, the below one, this is what happens when you run the Laplacian filter on top of this image. So you can see that the edges here were previously much more blurry, right? And they have become much more smooth. Why? Because if you place your Laplacian filter somewhere here, it will see that suppose this gray region that I'm pointing out. So this gray region is different, a little bit different from the white regions that are here. So towards the edge, and what that will do is this filter will ensure that, so suppose this gray region had a pixel intensity of 50, and these two had a pixel intensity of 200. So now it will ensure that this gray region becomes grayer and the white regions become whiter. So that what that will do is it will basically make your image much more sharper. So this is how. So every in normal image processing, the pixels that are there, all of them have some meaning. The filters that are there, all of them have some meaning, and they are definitely not pixel intensities. So you are basically, since if you look back at this image, you are doing, you are multiplying each of these pixel intensities with the numbers here. So they are basically adding some, they are basically like some weighted average of the pixels that you see. So the 7 will be multiplied by 0, 6 will be multiplied by -1, and so on. So it's like a weighted average. It basically leads to a weighted average of your the patch that is given here, and the weights will vary. I mean, they'll depend on the application you want to have. So suppose let me ask you this one very simple question. So can anybody tell me that suppose I want to instead of so this central pixel is 4, right? Instead of 4, what I want is an average pixel intensity across the entire patch. So in that case, what filter will I use? Can anybody tell me? So I have 4 here, but yes. So very simple thing. So a little bit, maybe a little, we can make it a little bit different. So Anirudh, what he's saying is that we can use a 3 cross 3 matrix of ones. So what that will do is that will just add up this entire matrix together, and all we need to do is normalize that with the sum that is there here. So that you, sorry, with 1 by 9, because there are 9 values here. So I hope the others got the point that if you want, so this operation that I talked about is called the smoothing operation. So what you are doing is, even though you have a 4 here, what you want is that your this pixel location, it should have something that is an average of all the neighboring pixels. So what you do is you put one across every element here in this matrix, so that all the so 7 into 1, 6 into 1, 5 into 1, and so on. So when you do the dot product and sum it up, so it becomes a sum of this entire patch, and then you just divide it by 9 to get the average value, and that you replace. So that is what is called a yeah. So that is what is called a linear filter. Okay, so and also we talked about Laplacian filters, where we showed that this is a very typical one, where we see that if you have a blurry image, it makes it a little bit more sharper. And the average one that I talked about, where you put ones everywhere across this matrix and just divide by 9, that basically what it will do is, at this particular gray portion like we looked at before, so what this will do is, this is a gray portion, like suppose 50 is the pixel intensity here, and here suppose, like I said, 200 something like that. So now what will happen is, you will add this 50, 200, 200, and the 9 numbers around this patch, and what you'll get is some average of this particular area. So that will make it what? It will make it a little bit more blurrier. So once we go through the code walkthrough, so in the second half of this session, we'll have a little bit of code walkthrough. So after that, I request all of you to go back and apply these average sort of filters, the other filters like Gaussian filters and all that we are not covering here. So you can just try them out and see how the images become blurrier. So the best way to learn the best way to learn image processing, if you want to learn it, is basically through more and more practice. So you can, if you can code it up, if you can play around with it, you learn more with more experience. Okay, so next, in the next part, we want this, right? So you have an eye image here, you have an image here, and what you want is, the images should be shifted by one, shifted towards the left by 1 pixel. So now I wanted to ask you, like, what should be the typical value of age here to make this happen? So again, like, can anybody comment on this? So again, going back, so what I want, this was my original image, and the original image will be there. There's no problem with it. All we want is that the pixels should be shifted by one position towards the left. So what can I, what can I do here? Okay, so 0, 0, 1, in what position do you want to put the 1? Can you write the entire matrix maybe, Anirudh, for the others to understand? Though, correct. So, like Anirudh said, so it's something like 0. The top row will be 0, 0, 0. The bottom row will be 0, 0, 0. And in the middle row, it will be 0, 0, 1. Why will that work? Okay. So, this is the answer, right? So, why will that work? Again, let's go back to our matrix. So, you have this, say, particular window. So, you wanted everything to shift by 1 pixel, right? So, this 3 should come in the position of 4. So if you have 0, 0, so the filter he gave, Anirudh gave was 0, 0, 0, 0, 0, 0 here, and there should be a 0, 0, 1 here. So this one gets multiplied with this 3, all other positions are 0. So the value corresponding to the central pixel will be 3 instead of 4 this time. So this is how we shift the pixels by 1 towards the left. Similarly, now you know what we'll need to do to shift the pixels by shift by 1 pixel towards the right or top or bottom. So you can do all of these manipulations through these matrices that we are calling filters. So these filters, they operate on your image, and then they manipulate the image in the way that you want. Cool. So next we'll cover this topic of image thresholding. So what we are doing here, image thresholding is what? So to make, in some cases, for easy manipulations, for age detection and other important applications, typical images like this, which are grayscale. So the values are from 0 to, the pixel intensities are from 0 to 255. So now what we do is, there's something called image binarization. Okay, so in the image binarization, what we have is, like the name suggests, so binary. So we only have 2 pixel values, 0 and 1, instead of 0 to 255. So you can see that while this was a gray image which ranged from 0 to 255, we have converted it to another image which only has 2 pixel intensities, 0 and 1. Okay, so now how do we do that? Okay, so there's a whole lot of algorithm to convert a given image into binary image, but here suppose we are telling you that, so the method to do this is called image thresholding. So thresholding means what? That okay, so yeah, some convention. So here it's written 255. So some convention says that it can be, the pixel intensities can be 0 or 1. Some convention says that they can be 0 or 255. Anything can be, anything is acceptable, but for binary images, you only have 2 intensities. That much you can remember. So to convert from here to here, this algorithm is given, which says that you're at any position m comma n, your intensity is 255. If in your original image for the same position, it was above, the intensity was above 100, otherwise you have 0, right? So all intensities that were above 100, you are making them 1, that is 255. All others are made 0. That's why the darker pixels have become 1, the lighter pixels have all become, the darker pixels have become 0, the lighter pixels have become 1. So this is called image thresholding. Okay, so can thresholding be implemented as a filter? So the answer to this question is yes, thresholding can be implemented as a filter. So we'll have to do some quirky things to make it work. However, is this a linear filter, right? So let's look at this. So there's some very simple things that we can do to find out whether a given filter is linear or not, right? So what is the property? So to understand whether a given filter is linear or not, we'll first see what is the linearity property of a filter, right? So suppose you have two images, A and B, right? And G is your filter, right? So if G is supposed to be linear, then this property should hold, right? So if you add the two images A and B, so that becomes A plus B, and you operate G on top of A plus B, that should be equal to G of A plus G of B, this summation, right? So it should I mean, if you operate it separately on A and B, then the summation should be equal to this particular quantity, right? So now, yeah, yeah. So now, say at a certain location, A of Mn is 90, B of Mn is 20, right? So 90 is close to 100 that we had talked about, and 20 is close to 0. So now, what is G of A comma N? It's 90 because it's less than 100. Okay, what do I do here? Let's ignore this one. Okay, so um, yeah, so this B of Mn is 20, like I say. So if you operate G on B of Mn, so G is again what? G gives you this value. So if a pixel intensity is greater than 100, it's 255, otherwise it's 0. So A of Mn is G of A of Mn is 0, G of B of Mn is 0, because both are less than 100. But now if you add them, so 90 plus 20, so that becomes 110, right? So this one. So now if you operate G on this A plus B, then that becomes 255 because it's more than 100. That means what? The thresholding operation is definitely not nonlinear. So this is how you can prove the nonlinearity of any filter that you take into consideration. Okay. So another question that comes to mind is, suppose you want to find the median of certain 3 cross 3 patch on the image. So even that can be implemented as a filter. So do you think that this median operation is linear as well? So the answer is that no, median operation is also not linear, but this median operation can be implemented as a filter. So I request all of you to go back and see the math behind it. So as to how medians can be thought of as filters and how they are not. So non-linearity part you already know from this proof how to show. So here also, I mean, in the similar fashion, we can see that median of A plus B is not equal to median of A plus median of. So here it's a typo. It should be median of B. Hence, median is not a linear filter. Cool. So this is what I had today in terms of theory. Others. So before we go into the coding part, so any of you have any questions, you can just ask me very quickly. Okay, so let's do one thing. Let's go through the coding part quickly. So yeah, so I let's do this once. Okay, yeah. So yeah, I'm assuming that the code is visible, and I'm also yeah, increasing the font a little bit. Cool. Okay, so assuming that most of you have some knowledge of NumPy and sorry, some knowledge of Python, I'll go through this code very slowly and step by step. So this is the part. So this is where we visualize an image and we try to understand what goes on inside an image. So the first step that anybody does, like in all programming, we import all the libraries that we want, and all of these libraries are very typical to visualization and images and how you process them. So this matplotlib is a library that is used to visualize any data. So you want to plot something, you want to visualize something. This data set, this particular library is useful. Also, we one thing to be noted for Python, especially, is that so Python by default doesn't provide us with any array. So Python has a list data set, but it's not an array. Now, there are other ways to convert a list into an array, but this NumPy package is a very, very well accepted, very, very popular package, which will, convert your list to an array, and you can, yeah, yeah, it will convert the list into an array, and you can do multiple things like matrix multiplication and matrix norm, I mean vector norm and all those things. So basically, NumPy converts the world of Python to the world of linear algebra, which you can use to manipulate your images and all. skimage again is another tool, another library that you use to read and input images. So we are importing this skimage library, and we are importing the IO part from it. So now let's first see how to read images. Okay, so we'll see what happens when we have an RGB image and a grayscale image both. So these are the images that we have. Okay, so okay, wait a second. Yeah. Yep. So to read an image, what you do is you have the path for it. So all you do is you do an io dot im read. Okay. So do an io dot im read, and in between brackets it has to be the image name. Similarly, for this is the color one. For the gray one, you similarly load the other image. Okay. So I request you to, I think the link for this is already shared. So make a copy of this. Don't change it directly. Make a copy of this. Suppose input your own image, input whatever you have on your laptop, and try and see whether you are able to read that image and visualize it or not. So now this image img variable that you have that contains your image, and all you do is you imported this matplotlib, like I said. It basically is a visualization or plotting tool. So you do a plot.imshow. So this plot.imshow is basically this is used to print the image on your interpreter. So this is what the image looks like, the color one. Okay. So now what do we know about an image? So image is nothing. So yeah, is there a question? Yeah, yeah. Go on. Yeah. I'll go into that. Yeah. Sure. Okay, so that's exactly the next point that I wanted to show you. So if you have this particular variable which contains the image and you print it, so this is what you get, right? So this is a NumPy array, and you can see the values. So they range from 123, 126, and so on. So these are the values, typical values that you see. So basically, this shows that your image is a this matrix is a contains of numbers ranging from 0 to 255, like we already established. So this variable, so when you open a image file and load it through skimage, that already converts your image to a NumPy array which you want to manipulate, and the proof of that is shown here. So if you do a type, so if you want to find the data type of this image, you find a numpy.nd array. Yeah. So, Mona, the I think the link is already shared, but I'll share once again. Don't worry. Okay. So now what we next see is that we showed you an RGB image. So that has to be of three channels, right? So we know that RGB images are what? H cross W cross 3, where H is your height and W is your weight. So once you type this image.shape, so this image.shape, because image is an NumPy array, this dot shape function gives you the dimension of that array. So if you print it, you see that for this particular image that we opened, it's 827 cross 1241 cross 3. This is the height, this is the width, this is the channel dimension. So channel dimension can vary across. So this format basically, the height, weight, and channel. This ordering varies from library to library. So if you want to use some other library like OpenCV or PyTorch, maybe you are using to open your image. So just check it out where your channel dimension is, and otherwise you'll start making mistakes. Right. So what are these? So why is this three here? Because you basically we display, or we represent color images using these red, green, and blue channels. So what we'll do is next we'll just so using these matplotlib functions, which you can look at later. So what you are doing? So if you look at just this part of the code, so your channel is in the third dimension, right? So you are taking the 0th channel, 1th channel, and 2th channel. So 0 stands for red, So that is given here, one for blue, two for green, and you are printing the individual axes, right? So instead of going to the looking at all the three channels at once, you are looking at them individually, and this is what it looks like. So these things, like I said, the more that you play with them, the more will you learn. So just go back and play with all these codes and like load your own images and have a lot of fun. The more fun that you have, the more you'll understand what is going on inside. So now next step is that let's look at the grayscale image. So this image underscore gray contains the grayscale image, if you remember, and you just plot it, and this is what the result is. So the result is a okay, yeah, yeah, okay. So the result is a gray image like this. So now if you directly print the grayscale image once again, so remember to do these things every time you play with your images. So what are the internal values and all, so you'll get an idea. So previously for the normal image, what we saw is that the values were integers, right? So they were from 0 to 1, 0 to 255, my bad. So here you can see that these values are no longer integers, they are rather, they look to be less than 1. So what has happened is, because there's only one channel, the sklearn, the skimage library has already converted this image. It has basically normalized your image from 0 to 1, which is a very common practice in image processing or computer vision, that you do not keep the values to be integers from 0 to 255, rather you normalize them such that they contain some value from 0 to 1. Yeah, okay. Right. So now again, let's look at the shape. So expected is that we do not have, would not have any channels here, and that is what we see. That the number of the dimension of this grayscale image is just 827 plus 1241. There's no third dimension. Right. So yeah. So this is a 2D matrix. Okay. So now uh, yeah, what we'll do here is we'll look at a little bit more in a little bit more details. So first, let's do one thing. Let's take another image. So forget about the previous images that we showed. And this image is of a horse, which you will find in the SK image library itself. So you can see this skimage.data.horse. So this is a pre-stored horse image that is there with SK image. And this is what it looks like, right? So this is the plot of the, or this is the visualization of the image that we loaded. And we wanted to print its shape, and we saw that the shape is 328 cross 400. So this is the proper grayscale image. So now notice one thing, that this particular matrix has no other color, right? So it's just zeros and ones, which is very similar to the one that we showed in the slides. So this is nothing but a binary image, like I talked about. So there'll only be two intensities, two pixel intensities present here. So plain white and plain black. So now, given this, so if we print this image, this is what it looks like. So this is the image so this is what is contained in this image. So let me accept. Yeah. Okay. So this is what is present in this image. So why are these all suddenly? So previously I showed you that the images were integers for the RGB ones, something decimals for the grayscale ones, but for the binary ones it's simply true and false. Why that is so? Because since we have already told that the binary images only contain two pixel intensities, so that's why storing them as integers is like a waste of space. So that is why binary images can be stored as a boolean instead of int, right? So that helps in the storage part of binary images. Yeah. Okay. Okay. So now, yeah, again, somebody had a question. Yeah, sure. Rudra, please. Hmm. Hmm. Uh, Come again? Just can you repeat the question once? Hmm. Yeah. Hmm. Not here because this is a Boolean array already. But suppose you have converted it to an integer array, and then you are applying some transformation. Then it can change. Here you are kind of like, yeah, you are ensuring that there are no other values, only trues and false. Yeah, 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 yeah. Cool, cool. Yeah. Okay. So yeah, so this part of the, so we are doing some fun stuff here once again. So basically, so you want to, so this is a binary image like I told you. So basically, people, I mean, this image is plotted in this way in 3D. So you can look, maybe I'll not go into this too much. You can go back and have a look at it. So basically, so this is the horse image, and in 3D what it looks like. So again, this is a interesting or fun experiments that basically people keep on doing. So this is a 3D projection of your image that was binary in nature. So yeah, this is again another fun experiment that you can try out. So now we'll look at even more interesting results that we have. So again, let's load a fresh image from the same SK image library. And now we'll do some. So again, this is not a binary image, right? So binary images we cannot play with, and we cannot transform them in any. Okay. So why is it showing this? Okay, let's not do this. Yeah. Okay, so now what we'll do is we have loaded a grayscale image in our this img variable, and all we want to do is we want to manipulate it a little bit. We want to do some transformations. So let's look at them one by one. The first line basically is saying that you plot the image as a normal grayscale image. Okay, the second line. Okay, so let's look at the image together with the instructions. Yeah, let's reduce the font a little bit. Yeah, this is what the outputs look like. So the first line, you are basically printing the image as it is. So this is the original image. So now you can see that in the second line, what you are doing is you are adding img plus 40. So what this statement does is it will add 40 to every location in your image, right? So if you are adding 40 to 40 pixels to every location in the image, then what happens is it just becomes a brighter version of what you have, because your intensities have all increased by 40, right? So be assured that yeah, I mean, for some pixels that were 255 here, that become 290, so 295 here. So you can see that all those pixels that were white, they somehow they are clipped in the image with increased intensity. So some libraries choose to keep 250, 295, or anything greater than 255 as 255. Here it seems that they have changed it to something like 0 or something. So different libraries have different ways of dealing with this. Okay, so now next thing, so you can see from here that this particular function, the function in the next line, so this basically flips the rows of the image. So that is given by this particular function. So anybody, so this is again a Python nitty-gritty that you should learn. So what you wanted is the image to be rotated on the row side using the rows. So assuming that this x-axis is the row, right? So uh, this flipped row image is a rotated version of this original image. So all you have to do is take the first dimension of the image, which is taken to be the row, and then do this reverse function, which is a standard in Python. So that gives you this image with flipped rows. And similarly, now this one, so this is this, while this looks rotated and a little bit unrealistic, this one is very funny, very interesting, because so this man was looking towards the right from the left, and now he's looking towards the left from the right. All you have to do is you have to rotate column wise, right? So to do that, what you do here, just note here that in this particular matrix that you have, You do not now, this time you do not want to touch the rows. So since the rows come first, you take them, you say, tell NumPy that I don't want to do anything with this. So you put a comma. So everything before the comma represents the rows where you are deliberately telling it that don't change it. And then you put this part, which is the basically the standard code for reversing Python. Reversing Python arrays. Right. Okay, so next we'll move on to something called point operations. Point operations means what? That you want to operate at every individual location, at every individual, location in the image matrix. So any ij point that is there in the image matrix, you want to do some manipulations with that, right? So now again we load a fresh image here using data.camera. So this is already there in the library, like I said. And you define these two variables, Imax equal to 255, Imin equal to 0, right? Now what you do is this operation, have a look at it. So now you know that in your image that you loaded here, so there the minimum value is 0 and maximum value is 255, like defined here. So now if you subtract this your original image from Imax and add Imin, then basically what happens is whatever your pixels were, you are basically flipping them, you are basically reversing them, right? So basically, in some sense, whitish areas become blacker and blackish areas become darker because you are reversing it. Okay. So if you are not being able to get this, then please go back and have a look at it. Yeah. Okay. So this is what you get out of it. So if you do this operation, so basically take the max value, subtract the image, add the min value, then you get a image like this. So the dark coat becomes white, the black hair becomes white, and so the whiter sky becomes dark, and so on. So this is how you. So again, this is a fun experiment that you can go ahead and try out with your own images maybe. So yeah, this is a fun operation. So just note that these two are constant values, this Imax and Imin. And so if you basically your NumPy is capable of adding, so you are subtracting your image matrix from a constant value. So NumPy is able to do that. So it will just convert this Imax into a matrix of constant matrix containing values Imax, and it will just subtract the image. And similarly, this Imin. Okay, so next we'll do some contrast stretching. So yeah, so let's read another image next. Okay, so this is again by going by the shape, it's again a grayscale image. So this image looks like this. So now we'll enhance the contrast of it. So we'll do so to do that, this algorithm is called full scale contrast stretching. So it's actually very simple. So what you want is that your okay, so this was your original image which we plotted here, and now let's print the minimum value of the matrix. And okay, so yeah, I think conceptually they are very similar, Justin. So this the image that you got, so some people even call it the negative of the image. So that's how I learned. So this you are basically, this was your original image, you are making it negative. It's you are getting the negative part of it. So you are basically making sure that everything is reversed. So I think yeah, I mean they are pretty similar things. Yeah. So, okay. So now you see what's the minimum and maximum value in this image. And you see that the minimum value is 61, maximum value is 250. So now so from whatever we know about images, the minimum value allowed for images to have is 0 and maximum is 255. So this particular image that we have displayed is not it doesn't have a minimum value of 0 and a max value of 255. So what full scale contrast stretching or linear contrast stretching does here is that it will convert your image in such a way that it will transform your image such that uh, your minimum value instead of 61 it becomes 0, instead of maximum, instead of 250, it becomes 255, right? So there's very, very simple formula for it, which you can go back and have a look at. So it basically, what it does is to convert. So again, point operations are what? You are basically applying a function on every pixel location of the image, right? So that is why point operations. So every point in the image, you are applying a function, the same function. So to do this, some simple math is required to understand what the contrast image formula is going to look like. But very simply put, it's something like this. So you basically subtract the minimum that you have from your origin of the original image from the actual image, and you basically make sure that the range, instead of spanning from 61 to 250, it spans from 0 to 255. Yeah. So it spans from 0 to 255. So this is what you ensure. And now you can see that once you have done this, your contrast has become so much better. So here, while the image was a little bit grayer, I don't know if it's very visible or not at this point, but yeah, you can, if you go back and see, you'll see that the darker parts of the image, they have become even more darker and so on. So this has basically enhanced your image much more, and it has increased the contrast of the image. So now after doing this operation, you can print the minimum and maximum, and you can see that they have become 0 and 255 like you intended. Right. So there are some other operations as well, like moving average and so on. So these are all local operations. By local operations, I mean that operations that you perform instead of. So previously, what were we doing? We were doing pixel location wise. So we had some function, and we were applying that function on each location of the pixel, and we were getting some transformation. So all of these, if you see, these are like, you are at every position in the image, you are applying a certain function. Yeah, you are applying a certain function, like I said, right? So here what you do is, instead of applying a function on a single pixel location, you are doing it window wise, like I showed you some while back. So here, yeah, so you take an image once again in this way. Yeah, you take an image once again using this using this particular piece of code, and you define a window size equal to 15. So now the next step, what they are saying, let's go look at it step by step. So you do some padding. Okay. So why the padding is, padding means what? Padding means adding some border pixel to the image. So padding is something that is very, very critical in the, like it says that it's very, very critical in deep learning as well. So you'll get to know about it more in the uh, next sections or next weeks, upcoming weeks. So basically, you can, in a nutshell, it basically means that so again, let's if we think about the image that we had in the slide. So normally, if you perform some windowing function, like we saw during the linear filter portion of the lecture, uh, if you observe correctly, you'll see that if you apply a filter on your image size basically shrinks, it decreases, right? So if you want your image size to not decrease, then you have to apply some padding, which basically means that if we look at, suppose if we look at this image, padding will ensure that your image becomes a little bit, so the borders here are increased a little bit, so that your image size is maintained once you apply the filter, right? So let's not go too much into the math part of it. Just understand that we are doing this in order to successfully do the windowing function. So some pad sizes, so all of this you will get to know in much more detail in the deep learning part of the course, which is coming up in the coming few weeks. So you have this pad size. So given an image, you have to figure out from beforehand how much you need to pad it from from the different corners to make it of the same size, to make sure that a windowing function doesn't change its size, right? So now what it says in the next step, initialize an array to store output of moving average. So what you do is you have a you have the image img, and now basically you have a new matrix which is of the same shape as img, and you are filling it with zeros. That is what np.zeros does, right? Next is, you have already calculated what is the ideal size for your image, so that padding it with that size, make sure that your windowing function, um, is not reducing the image size. So based on that, what you do is you apply this function. So this img underscore padded is the padded version of the image. So numpy, like I said, it's so powerful that it also provides you with the pad function. So np.pad, so it will just pad your image, and so you give the image as input, and you also give the padding size, so how much you want to increase on all sides. And yeah, and what do you want to, so again the question is that if you have this image and you want to increase it, then what do you want to fill it with? So generally people fill it with zero. So if you increase a, suppose this was a like it looks like a 550 cross 850 dimension image. So if you want to make it suppose 551 cross 851, then what you need to do is, the extra portions that you added, you can put simply put zeros there. That's it. Okay. So now your okay. So what was the original? Okay. So yeah. So after doing this, your image size becomes 526 by 526. So I mean, yeah, yeah. So this is for the new image, right? And so you now plot it. So it's the same image, and you can see that the borders have become a little bit wider because you have added that padding towards the to the all four corners of the image, and you filled them with zero. And now, so this was a moving average function that we had. So what you do is, so this particular section, right, local operation. So this is not about, you having a filter and then doing a dot product or those sort of things. This is about that given this sort of image, what you'll do is you'll again divide the image into patches like we were doing, but you won't have a filter this time. All you'll have is take this particular patch, compute something out of it, and replace whatever value you have with the sorry, replace this patch with whatever value you computed. Okay. So similarly, I mean, like based on what I said, it's doing the same thing. So for all, so you visit all the rows and columns of the matrix. You cover all the rows and columns of the matrix, and you go to the image underscore padded one, right? So see that here you are not using any filter. Like I said, all you are doing is you are visiting the I from the ijth location of the image, you are visiting the window size that you had. So 15 was the window size, if you remember. So you visit this. Okay, so this is the patch that you take. So this is the, suppose a certain patch here that you took, right? And on this image moving average at the ijth position that you have selected, all you do is you put the mean of this particular matrix. So you, whatever, so instead of a linear filter, you have a function and you compute it on the window itself, on the image itself, on the image patch that you have chosen. So this is what is known as this local operations. Okay, so simply to a, so at the end we see that the plot looks something like this. So yeah, okay. So now that we have ended this, so I'll ask this one last question. So this is all I have for today. So can anybody tell me why this image got converted to this image? Correct, correct, correct. So I hope the others also got it. So all you are doing is at every patch, you are basically the average filter that I explained to you. So that was uh, itself adding all the pixels, and that was a way of adding all the pixels and dividing by the total number of pixels. So here we are already doing that in the form of a function. So we choose a certain patch, and then we replace that patch with the mean of that patch. That is why. So the moment you replace something with its mean, that means what? That in every region where there's a change like this. So this was white, this was fine, but suddenly when you come towards this coat part, it has changed from white to black. So now, if you do this averaging, you have these white pixels, you have these dark pixels, and an average becomes somewhere in between. So this is because of this, your image looks something like this, right? It's a blurrier version. So some message I got. Correct. Good. So yeah, so this is all I had for this week. So hope to see you soon in the next week. And yeah, in case of any questions and doubts, please let me know. And also, so for the next class, we'll also still uh, we'll go through some parts of this image processing once again, and maybe from 2 3 weeks onwards, we'll go into proper deep learning. So thanks everybody for joining. So this is what I had today. Yeah. So yeah, it's already shared, but yeah. For everybody who is looking for the file, this will be shared. And so once you have it, make a copy of it on your own drive. And so this is a very, very beautiful collab notebook where you will get all the very starting concepts of what an image should look like. You can play with it, you can do anything you want. Like somebody asked me, what will happen if I make transformations to this binary image? So why don't you go ahead and see what transformations you can make, whether it works or not. So all of those playful things you can do. So have fun with it. So before going into proper deep learning, this is how you should learn what an image looks like and what an image basically represents. So yeah, this will be uh, okay. So somebody is asking for okay, good resources for brushing up on linear algebra, differential calculus. So differential calculus. Yeah, the whatever you'll have in the deep learning part, it's pretty simple. You can just go through some basic formulae on Google. And linear algebra, if I find some good resources, I'll let you know. Okay, so Justin says how to load an image in Drive and access it. So okay, so for that, there's some small. Okay, so one easy thing can be that avoid. So just download this Google Colab, and you can run it on your local system as a IPython notebook. That is one thing. The other thing is that you can just follow Google, so it will tell you, like, you can store these images probably on the drive itself. But how to access Drive from Colab? That is something that you can just Google and find out. It's pretty simple. Yeah, so like Sharad said, yeah, it was my bad. So I should have mentioned Gilbert Strang. So yeah, so whoever asked for linear algebra, one very, very, very good resource, if you don't want to read, is the videos of Professor Gilbert Strang. So they are available on YouTube as well. So that will be enough. So just go through it. It's actually very, very beautiful. So everybody should go through it once. So yeah, that's my suggestion for linear algebra. Yeah, Rudra, you can. Hmm. Hmm. Um, Idea is fine for now. So if you want to learn like classical, so see, deep learning, you'll get to know that deep learning is a system where you need lots of data, and then you have to train a model on the data, and you can classify or get some results. So Fourier and all, why we encourage people to learn is because here you'll get to know, like, some method which is which doesn't need any data. It works on everything. It has not been trained or anything. It's pure mathematics, but it works on everything. So for this course, I think it's okay to just have an idea, but for your own benefit, since you want to learn images and I mean, deep learning for computer vision is the course's name. I would suggest that you look into Fourier a little bit more to have more intuition on it. But yeah, for this course, it's not really that much required, so you can just have an idea. Yeah. Yeah, so I think Divya, your the applications of these transformations, yeah, you most of it will be covered in the classes only, and some applications upfront I can give you from here. So, for example, yeah, very often. So this particular these transformations that you see, flip rows, flip columns, this is actually pretty used in deep learning in something called data augmentation. So deep learning is a very so let's not go into that. Let's give Cert the time to cover it. And another some other applications can be that these are if you want suppose your image is like this, your original image is like this, which is suppose not it's not the very highly contrastive image, so you can change the contrast of it. So you guys all do it on, I mean, you guys all use it use many filters on your phone, right? So it's the same thing. So those filters are a complicated version of what you'll get to know here. So how to increase the contrast, how to increase the sharpness. So in some slides I showed, I think that uh, yeah, some there was some blurry part, blurry edges, how you make that blurry edge go away. Sometimes also there's so some images have some, so images may contain noises as well. So the averaging thing that I showed you, so this one, so this averaging part of the so this averaging functions can be used to remove those noises, because suppose there's a very small noise somewhere in this corner of the image. So if you do an average across a window, then basically that noise cancels out because you're averaging across a big neighborhood. So all these transformations have many applications. One which you people use daily on your phones, whenever you take an image of a picture of yourself, you apply filters to make yourself look better, and yeah, I mean, the images, the photos look much more better. So that is one application. The other application is to enhance the contrast and all, so that you get to understand the image, so that your computer gets to know understand the images in a much better way. Yeah. Link of file, Farooq, do you mean the this Colab notebook? Then yeah, you'll get it. I'll share it. It's already shared, but yeah, I'll still see if I can share it once more. So don't worry about it. Yes. So yeah, the video is already being recorded, so it will be uploaded once the session ends. So any other questions from anybody? Yes, so this is the first session that we conducted. So all the sessions will be so the TAs will work towards interacting with you live and trying to understand where you are getting stuck, or maybe revising some parts that have been taught by sir in a certain week. So it will be like this, that in a certain week sir teaches something, and in the can you mute yourself, please? Okay, let me do it. Yeah. So in a certain week, we sir is going to teach you something, and in the coming week, we'll follow what sir taught, and we'll revise some of the concepts, make you more aware of the code, and so on. Yeah. So yeah, you'll get all the recorded sessions. Don't worry about that. So three TAs will be taking individual sessions. So you can attend any of them. You can attend multiple of them. You can look at them later. Anything that suits you. Uh, this recorded class you will get. I think NPTEL's website will show the recording. I mean the links for the recorded classes. So they'll be uploaded on YouTube as well. So yeah, everything will be available to you, starting from the slides to the code that I shared and the video link. So everything will be there. Yeah, like I said, I mean all three. So the plan is that for the first few weeks we'll teach the same things, the three of us, and based on your requirement, how the attendance looks like, we'll after that we'll simply take a call from there. So whether to teach the same things or different things. So based on your time availability also, you can join any of the slots, or you can join multiple slots as well. So that's all fine. Cool then. So if there are no more questions, let's end today's session. Yeah. So let's meet next week then.